Hi guys, last video we saw how we do analysis using conventional shell elements in Abaqus. This video will be using a technique called as continuum shell elements. So let's quickly make another model with the continuum shell elements. In previous one we used surface, but now we'll be using solid. That's the first difference between the continuum and conventional shell modeling. Dimensions are 500 cross 2 as a cross section. Okay, cross section is ready. Let's quickly go and done 500 mm. So our plate is ready. Just to give you brief idea what exactly is the difference between the continuum and conventional. So in conventional we have all 6 degrees of freedom. I have put a beautiful pictures from Abaqus documentations. All right, continuum will have only displacement degrees of freedom. Like we saw in the previous one, we used a reference surface, but this time we are using a 3D body itself. And another difference is the directions of the positive normal. Those depends in the continuum shell based on your nodal connectivities. For example, if you are having a um, cylindrical object, then based on the nodes and their locations, the normal will be defined. So this is why usually people would prefer to go for structured meshing or sweep at least, because otherwise your normals would be affected, and that would become a problem if you're doing even composite analysis. Okay, let's quickly go back to our part and define the property. We have to have a steel material. You can skip this section if you have already aware of how to define the material properties and all, but now you have to actually look at section manager. So last time we used the shell homogeneous, this time also because it's a conventional shell or continuum shell. So we use section based on mm, shell itself. If you are going for a 3D and all, then you will go for solid. Shell thickness is how much? 2 mm. Okay, let's keep okay. Let's quickly assign this section to our part. Color is changed to red, green, and next step is to go for meshing. Okay, we have already structured as I was showing. So structured sweep or bottom, whatever you want to choose, you can choose hex dominated, tet, or those things. Okay, let's give 10 as a size or 15. Let's keep 10. Okay, and we'll do the meshing. Now, if you're not sure what is this mesh, because is it a solid or is it conventional or it is a continuum, you go to the query option over here and then click on the mesh and entire part done. This is C3D8R, which is solid. So that means this is not continuum elements. What we have to do, SAR, assign element type. So here you have to see, you see, this is 3D stress family, but we don't want that. We want continuum shell. And interestingly, we don't have quadratic order for this. Okay. So continuum shell, click OK, and we must have it now. Go back to query or information and click on mesh, entire part done. See, we have now SE8R, that is the description for the continuum shell elements. Okay, we have our elements. So here one thing you can do is assign this stack direction, which I was talking. For that, you have to choose the top surface. Let's keep this as top surface. Yes. Okay. Now if you see, you will have brown as top and purple as bottom. So our stack direction is defined in this way. You have to do that. Otherwise, your results will not be really uh, you won't be visualize them. Okay, so quickly bring this part to assembly. Now most of the work is done. Now this is the repetitive task which we use in all other models. Static done, non-linear geometry. And all right, so this is a 3D part. So what, how do we apply the loads now? We have to again make a reference point here. or else we can apply a pressure load on this particular end, but we'll keep the same method we have been using so far. mm, no new creativity, let's not go for that. Okay, at this location we know this is 500 from the origin, comma 2. Okay, my bad. So in y direction it will be 1. Our thickness is 2, right? So half center, and in z direction we want from our coordinates it should be at 250 to become at center. Let's see. Yes, it is between these 2 points. So interestingly, or else you can do a partitioning and then choose that particular point directly also. That is another option. Okay, so let's go to the constraint coupling, and our control point is reference point, and done. Surface is surface. Okay, we choose surface, surface, done. Let's keep structural coupling. You are as per the global coordinate system. Cool. Okay, our coupling is ready. The only thing pending is now applying the load. Let's quickly go there. Concentrated force. In case you want to apply a moment or so, you can make a reference point like this and then apply moment on that. Okay, based on your requirements. So in x direction, 1000 Newton force. All right, force is done. Okay, so what next? Boundary conditions. Let's keep the similar to the previous model what we did. The region we want is, we choose this surface, done. U1 axial in the U2, and let's keep UR3 also 0 and see what happens if any error comes. Okay, let's delete these previously done. Make a copy, model 2, choose it, shell, continuum 1. Okay, submit. Let's wait. Hopefully it won't show any error. So our analysis is completed. Let's quickly go for the results now. Uh, we shouldn't be expecting the same, but it is quite similar. Wow, interesting. So that's how it works, I guess. So you see von Mises, and if you look at S11, very similar result. Interesting, more colorful. If you refine your mesh, you'll be able to get more curves here and all. But yeah, this is how you do analysis using continuum shell elements. Okay, so that's it, I guess. Okay, thank you guys. Thank you.